Hello everybody, welcome back. My name is Michael. Thanks so much for joining me today. Today we're going to be jumping back into Harvard CS50X 2025 Lecture 5 on data structures. This is week 5 of Harvard CS50X. Let's jump on in.
All right, so let's clean up one other detail here. Let me propose, whoops, spoiler. Let me propose that we consider this question. So we've just built up a linked list now that is appending nodes to the list, upside of which is that we're actually preserving that first in, first out property potentially, if we care about that, because it's 1, 2, 3 now instead of 3, 2, 1. However, have we made a dent in the running time? I don't think so, because if anything, it's gotten worse. No longer are we inserting in constant time. Now all of our appends require big O of n time, just like our searches, because we have to constantly search from left to right, search from left to right. Now, admittedly, we could do a minor optimization. We could just have another variable that just always keeps track of the tail of the list. And that is a perfectly valid solution. It's going to cost us a little more memory, but that's valid. But in general, when you're appending something to a list and you're implementing the list as minimalistically as you can with just one pointer called list that points to the beginning of the thing, then arguably it is going to be big O of n. But if that matters is really a question for the problem you're trying to decide. But I think there's one thing we should still do before we move on past this code. Now I have a program that indeed builds a linked list by keeping everything in the same order in which we inserted it. However, I have not yet done anything about actually freeing the memory that I've actually been allocating all this time. So let me propose to at the bottom of this program, before I return 0 and say I'm done successfully, let's just propose that some more time passes in the sense that maybe there's more code going on that's more interesting. But if and when I do want to free this linked list, it's actually fairly straightforward. I can specify that I want a temporary pointer called PTR again, for instance, set that equal to the start of the list. While that pointer is not equal to null, what I want to do is this. And this is where you can potentially get into trouble. I could free the current pointer, and then I can update pointer equals pointer arrow next. In other words, if I want to free these elements, I could simply iterate, I can simply iterate over all of these addresses from left to right, freeing the pointer and then updating it, freeing the pointer and then updating it. And that's how I move my finger from left to right. This is a problem, though. It's subtle, but as soon as you have freed an address in memory, you may not touch it again. You can think of it as the operating system immediately might do something with it, and it's not yours to touch anymore. Therefore, on line 59 at the moment, it is not allowed for me to go to that address, check the next value, and actually update pointer accordingly. It's too late for that, because in line 58, I already said operating system, I'm done with PTR, the address therein. But there is a simple solution, even though it might feel like things are kind of escalating. If I'm not allowed to touch pointer after I have freed it, but I really do need that next address, that's fine. You can simply create another pointer called next, for instance, set it equal proactively to the next field, then free pointer as you intend, but don't touch pointer again. Just touch the temporary variable that you created. So when you free pointer, free is not super powerful, whereby it's just going to iterate over the entire data structure you've created. It is simply going to undo one of your mallocs. Each time you call it, undo one, undo one. So if you want to undo all of them, that's up to you and me with our while loop here to iterate from left to right, freeing the node, then moving on to the next. Freeing the node, move on to the next, until we hit the end of the list. And we don't need to go any further. So there's still one bug, and I'm going to wave my hands at this one. But up here, recall, we did use malloc before. And it might have been the case that this very first call to malloc failed, in which case, OK, fine, we return 1 and we're all done. But if you imagine in your mind, what if the first call to malloc succeeds, the second one succeeds, and the third one fails? You can't just abort the program on line 20 and be like, oh, well, I'm out of memory at this point. Technically, before you return, I should free any memory already mallocked. And I'm not going to bother doing this now, because this is going to add undue complexity. But that's the sort of subtlety that starts to get involved when it comes to memory and memory management. And in fact, among the motivations in a couple of weeks' time when we transition to another language called Python is that if like you're just getting confused by this, you're zoning out, it's getting way too complex. Like a lot of people in the world feel that way. And it's so easy to write buggy code. It's so easy to write dangerous code in C that among the reasons for other languages like Python and JavaScript and the like to exist is that we can abstract away all of this memory stuff that you and I only have to struggle with for one more week. But even these details will still be there, but someone else will have done that heavy lifting. And you'll just use languages that take care of all of this complexity for you. So hang in there for this 1 week when we do sort of cap things off with these concepts. But rest assured that we'll soon be able to abstract those away as well. Any questions then on what we've just done here by freeing the memory we allocated? All right, rather than type this one out, I'm going to show one final version of this linked list implementation that's actually going to be a little smarter still. So if you imagine a scenario in which you don't really care about, you don't want the thing reversed, but you don't really care about the order in which things were inserted. What you really care about is sorted order, so that no matter what order you insert integers in, you want them to be sorted from smallest to largest. And you want the code to just figure out where to insert them, at the beginning or at the end, or heck, maybe even in the middle. So for instance, if we have a linked list that starts with the number 2, I want it to look like this in memory. If, though, I then insert the number 1, I want it to go before the number 2 so that the thing is kept sorted. If I then insert the number 4, I want that to be appended so it retains sorted order. And lastly, if I insert 3, I want that one inserted in the middle. And this is one that I'm going to sort of pull out of the oven already made, because this is where code just gets to be a pain in the neck. Why? Because, my God, there's so many different cases to consider. If I rewind here, there's the first case where the list is empty. And thankfully, that's actually pretty easy. Just plop it at the beginning of the list. Prepending, also relatively easy. We saw that before. I can just prepend it to the start of the list. Appending's not that hard, but now I'm doing 3 things. So I'm sort of combining all of these past examples into one so I can append it to the end of the list. The one piece of code we haven't written yet is how do I deal with like inserting the 3 in between the 2 and the 4 without orphaning the 4, so to speak? Well, let me just reveal how we would do this, even though you yourselves won't strictly have to leverage this in your own code. Let me go in a moment back to VS Code, and what I'm going to open up here is another version that already has some comments in place just to help guide us. So it's almost the same from the start, whereby in main, I initialize list to equal null. I then, in my loop, am going to proceed to build a list of size 3, just for the sake of discussion. I have the same code as before, whereby I malloc one of those nodes, make sure that it's not null before proceeding to get a number from the user, and then proactively initializing the next field to be null also, so there's no garbage values in this world. But here is the beginning of those several cases that we just saw pictorially on the screen. If the list is empty, easy peasy. I can just set list equal to n as we did earlier. So I've plucked that one off. But notice now I've got an else if. Why? Well, if the number I'm trying to insert belongs at the beginning of the list, that is, if I want to prepend this thing, OK, I can steal some code from earlier, update this node's next field to be whatever the current list is pointing at, and then change the list to be this new node. So that's the same logic as before, whereby I want to prepend a node. So this is like starting with just the number 2. I notice that, oh, shoot, 1 is less than 2, so I want to put the 1 there, AKA prepend. All right, there's another else here. And inside of this else is actually a loop with its own conditional. And this is, again, why I'm not doing this one live. So else, it's got to be at the end of the list, or it's going to be in the middle somewhere, depending on what number is inserted. So let's start a for loop, whereby we iterate over this whole existing list. This one's actually pretty easy. If we have reached the end of the list, as would be indicated by finding a next pointer equaling null, OK, this one, too, is fairly straightforward. Then change the next field to be the address of this new node, and then break out of this mess altogether, because we are done. This is like, in our picture here, having 1 and 2 in place and realizing, oh, 4 is bigger than 2 and 1, so it should be appended to the end of the list. It's the middle case that's kind of a headache, and that's the final flourish here. If I'm in the middle of the list, what do I want to do? Well, here I'm checking this logically. If the new node's number is less than the next node's number, so I kind of have to look ahead to realize, OK, I found my location in memory. I want to change the new node's next field to point at the current node's next field. That's like, in this picture here, updating the 3 to point at the 4. And then in code, update the current node's next field to point at n. That's like updating the 2 to point at the 3. And then, thankfully, break. I can get out of this mess again because I've handled the 4th and final situation. So again, with time, with comfort, with practice, like you too could like write code like this, but it really speaks to the complexity of trying to build up a fairly sophisticated data structure correctly in a way that uses all of these building blocks, but doesn't run afoul of leaking memory, orphaning memory. And this is why memory is just hard, because you have to worry about all of these little details. Questions then on any of these particulars?
Interesting.
Up until now.
It's a lot of information here.
Okay, I'm happy to say that everything here on out is going to be much more conceptual and much less code-oriented. But in the meantime, we have some delicious Halloween candy, and we'll see you in 10. All right, so we are back, and I admit that like the code that we just wrote to build a linked list, absolutely complicated, but representative of how you can indeed stitch things together in memory and build more interesting structures. And so here on out today, let me propose that if you're at least on board with this idea, that with some kind of complicated code, but with the building blocks of pointers and the C syntax we've seen, you can stitch together data structures in memory as you see fit. Let's just take for granted then that we could implement the underlying implementation details for the following alternative structures. And indeed, let's see if now we can draw some inspiration from the world of arrays, which were really appealing now in retrospect because they're simple, they're fast, they're contiguous. Like it was pretty straightforward way back in week 2. But let's kind of mash together arrays with this idea of linked list, or at least more generally, stitching things together, because maybe we can kind of get the best of both worlds. Because arrays, recall, give us contiguousness. That means we can potentially do binary search, especially if the data is already sorted. But of course, we paint ourselves into a corner with arrays because they might not be big enough for future data. So then we introduce linked lists, and linked lists are wonderfully dynamic. We can make use very creatively of memory. But with the catch with linked lists, of course, is that we're using extra space. The code got more complicated. So it's sort of the seesaw going back and forth as to what we actually care about. Well, it turns out that a very common data structure in computing is that known as a tree, sort of like a family tree, which we've mentioned before, where you sort of have this upside down tree structure where a root is so-called up here, and then you might have children and grandchildren and so forth. So it sort of grows on the screen top to bottom, much like a real tree sort of grows bottom up. But a tree, as we'll soon see, is sort of a two-dimensional data structure, whereas everything we've seen thus far is pretty much one-dimensional. Like an array is just left to right, and even though, yeah, linked lists can kind of go up and down and around in memory, at the end of the day, it's still a left to right linear or one-dimensional data structure. So what if we start to use a second axis, so to speak? Well, it turns out there's specifically a type of tree in the world called a binary search tree, which is this two-dimensional tree-like structure that you can actually perform binary search on. Because we did pay a price, too, with linked lists, you can't do binary search on them. Even though you get all of the upsides we discussed, the flexibility, the dynamism, why can you not do binary search on linked lists, might you think, based on how we've drawn them thus far? Yeah?
There's no mirror.
Exactly, because they're this long string-like data structure that you can't just go backwards on. I said, like, unless it's a doubly linked list, you can't go left and right. And there's no mechanism for jumping to the middle, right? No matter if you have arrows going left or right, the only way to get to the middle is to sort of traverse, frankly, the whole thing, figure out how long it is, then do it again 50% as much time to get to the middle. So that doesn't seem like very instant, constant time access. So long story short, on linked lists, you cannot do binary search, which means the best we're really going to do for most of those operations is big O of n, unless we do the whole prepending thing and achieve some constant time access, but that would seem to get us in trouble by slowing down other operations eventually. All right, so what is a binary search tree? Well, here's an array, as we've seen in the past, this one with 7 doors, if you will, but I've deliberately drawn it very one-dimensional. But let me color code this a little bit so as to highlight where the middle is, where the middle of the middles are, and where the middles of the middles of the middles are in this case. So we now have 3 different colors on the screen here, whereby the 4 was the first middle, the 2 and the 6 were potentially the left middle or the right middle, and then the 1, the 3, the 5, the 7 are similarly in the middle, depending on whether you go left or right. But I'm going to draw it this way because let me propose that this is an array at the moment. So we do have the ability to do binary search, but we don't have the ability to grow or let alone shrink this structure. But suppose that's a goal. We'd like this thing to be able to grow and grow and grow and maybe shrink over time. Well, what if I redraw this array by using some pointers in memory, kind of like this? I've just kind of exploded it vertically so that you can see more clearly that we actually kind of do have like a family tree-like structure here. If we think of 4 as the root, and 2 and 6 as the children of that root, and 1, 3, 5, and 7 as the grandchildren of that root, so to speak. And in fact, if I draw some lines to make this more clear, I indeed think that's what we have. Now, at the moment, I've drawn things more abstractly. I'm just using simple squares now. I'm not drawing rectangles with numbers and pointers. But these arrows do imply that each of these nodes containing a number also contains not even 1, but 2 pointers now. And in fact, that's where we get our second dimension. Suppose that each of these nodes, these containers for data, contain not just a single pointer, but 2 pointers, one for a left child, so to speak, one for a right child, so to speak. That would seem to give us the ability to build this thing up sort of 2-dimensionally in memory. And what's the implication of having built this up in this way? Well, how much time does it take to search this data structure now? Well, I can still do binary search even though pointers are involved, because so long as you keep track of the root of the tree always, with like one special pointer called root by convention, well, I can decide whether the number 5 is in this tree by starting at the root. And I know that 5 is obviously larger, so I can follow, instead of jumping to the middle of the middle, I can literally just follow the arrow to the right child. Now I know 5 is less than 6, so I can just follow the arrow to the left child, and voila, there is the number 5. Or maybe it's a dead end, in which case 5 might not be there. But I can implement binary search not even with doing arithmetic like in the case of arrays. I can just literally follow these arrows so long as I've built the data structure in this way. Now, how could I do this in code? Well, here, we're not going to write actual code with VS Code, but here is how I might implement a data structure for this in memory. Well, I could redefine the notion of a node as being no longer a number and a single pointer to a next field. This was how we defined earlier a node for a linked list. But let's reuse the notion of a node as just a container for data and instead build a node for a binary search tree, as we've just shown. Let me make a little more room vertically there, and let me propose that a node in a binary search tree that looks like the colorful picture should have one pointer called left, another pointer called right, that are going to literally point to other such nodes. And if it's null, that just means you're a leaf of the tree, which means you're at the very bottommost level with no additional children. So this is indeed exactly how you could build, using the same building blocks as before break, a more complicated 2-dimensional structure in memory, but gain back the ability to use binary search, which means now our running times are back in play, such that a data structure like this can finally give us, big O of log n running time. But what's the downside? If I'm now pitching this as like you want binary search trees now instead of just arrays or just linked lists, because you get back binary search, but you still have the dynamism, the growability of a linked list, what's the downside of what we've just done? Yeah, I'm just wasting more and more memory. It takes up more memory because I have not 1 but 2 pointers now for every node, which might be problematic, might not. It's really a design decision ultimately. But I will stipulate that this is very common design when you do have a structure in memory where you do want this kind of ordering to it, and you don't want to waste time like we saw with arrays, constantly copying or moving things back and forth around in memory. What's nice too about 2-dimensional data structures like the binary search tree, and binary search tree just means, to be clear, that you can do binary search on it. Why? It means that every node's left child is less than the root, and every node's right child is greater than the root, or equal to, technically, would be allowed as well. And that's, in fact, a recursive definition, because why? I can apply it here. The left child of this node is smaller. The right child of this node is smaller. The left child of this node is smaller. The right child, sorry, meant to say larger before. The left child of this node is smaller. The right child of this node is larger. So that is true for every node, including the leaves that just happens to have no children. So it certainly doesn't violate that same definition. So anytime you have this sort of recursive structure, just like the Mario bricks a while back, so can you use recursion in code. So I'm going to show code, but we're not going to write code. We're not going to run code. But here's code using recursion to search a binary search tree. So think of this as the implementation of binary search, but on a two-dimensional tree structure instead of an array.
Base case would be
if you pass in a pointer to the tree itself, so a pointer to the so-called root, and you give me a number you're looking for, here is how I could search a two-dimensional binary search tree that someone else has already built. I can first pluck off the easy base case. If the tree you've handed me is null, well, I'm just going to return false. Obviously, the number is not in this tree because there is no tree. That's easy. Else, if the number I'm looking for is less than the current node's own number, think about that root. So it might have been that first number in the tree, like that's like the number 4. Think of that as the starting point. So if the number we're looking for is less than the root's number, well then, let's go ahead and search the left subtree for that same number. Else, if the number we're looking for is greater than the current node's number, well, search the right subtree for that same number. Else, final case, if the number you're looking for equals the number in the tree, the node that you've been handed, then just immediately return true. You found it. And this is an unnecessary piece of logic. That can just be our else condition there. So just like the phone book back in week 0, where we were dividing and conquering by splitting the thing again and again and again, that's literally what we're doing here. Even though I'm using search here and here in my search function, aka writing a recursive function, every tree I'm passing in is getting smaller and smaller and smaller. So if we rewind to the picture, it's like starting here and then deciding, oh, wait a minute, I'm looking for something over here, so let me just kind of snip that subtree and focus only on this one. And then snip, 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 and you're essentially halving the size of the tree each time, just like we were halving the size of the phone book. So we're already starting to sort of reuse ideas from back there in week 0. Well, what more can we do here? Well, let me propose that with binary search trees, we now have the ability to not only gain back binary search, but to trip over ourselves again by introducing a new problem. Like, it seems straightforward that my binary search tree as of a moment ago was beautifully balanced. Like, this is a nice logarithmic data structure. And in fact, therein lies the halving. Because you are splitting each node into two children, that's like pulling up these nodes much closer to the root than they would be if it was just a long stringy array or a long stringy linked list. The height of this tree, in other words, is log base 2 of n, where n is the total number of nodes in the structure. But I had to go to great lengths in making this slide, but also in code. If we were to write the code, we'd actually have to jump through some hoops to make sure that when we insert numbers into this structure and when we delete numbers from this structure, that everything stays nicely balanced in this way. But let's consider a sort of a perverse corner case whereby the numbers you insert, one after the other, just happen to be in unlucky ordering. For instance, suppose I insert the number 2 first. OK, easy. It's the root of the tree. Suppose then I insert the number 1. That's easy. It gets to the left. Then I insert the number 3. I'm getting really, really lucky. So far, so good. That would lead to a very balanced tree of height log n, because everything's nicely balanced. But what if it's not that simple? And indeed, we have this perverse case whereby I insert the number 1. OK, no big deal. It becomes the root. OK, I insert the number 2. OK, no big deal. I don't have a third node yet, but that's not problematic. But what if the next number I insert is a 3? Well, if I want to maintain the binary search tree property that every node's left child is less than and every node's right child is greater than the value in the node, I can't put 3 here just to keep the thing balanced. Like, that would throw everything off. So 3 has to go there. And in your mind's eye, continue this logic. I insert 4, and then 5, and then 6, just because I get unlucky and I get this sequence of numbers, or the user's being difficult and giving me the worst case scenario. What is my binary search tree effectively devolving into?
A linked list.
A linked list. And so the catch with binary search trees is that even though, if they are nicely and beautifully balanced, do allow you to do binary search and achieve log base n log base 2 of n running time, you have to put in some effort to ensure that it actually does, in fact, stay balanced. So in the worst case, inserting into a binary search tree could actually be linear, because it just gets long and long and long and stringy with just one perverse branch, unless you're smart about it. And in fact, with that previous picture, you know, there's clearly a solution here. Like, what would you do if this is what your tree was devolving into? I'd kind of get in there and kind of rotate it around there so that 2 becomes the new root, and then 1's a left child, 3 is a right child. But you can kind of imagine from before break, oh, now someone's got to implement that code. And people have. And that's actually a discussion for higher level algorithms classes, how you can maintain balanced trees. But it does involve some cleverness with the pointers and updating things and essentially rotating the tree around if it starts to get too long and stringy. And so in general, with binary search trees, if you do make that optimization and you maintain balance, it does not devolve ultimately into big O of n. You can ensure that it stays in log of n for not only searching, but insertion and deletion as well. So long as you don't just blindly stick it in, but you kind of rejigger things as needed to keep things nicely balanced. OK. So another data structure is that of a dictionary. And a dictionary is actually something with which we're all familiar with in the human world, whether it's in English or any other human language that associates words with definitions. You can kind of think of a dictionary as being like this 2-column chart whereby you've got a word on the left and its definition on the right. Word, definition, word, definition. Turns out that this is actually a wonderfully useful data structure to have access to beyond lists, beyond arrays, beyond trees even. The ability in code to associate words with definitions, or more generally, what we'll call keys and values, is just super useful. Why? You can implement a phone book as what really is a dictionary. Instead of thinking of it as a word and a definition, think of it as a name and a number. And throughout the world, there's just such a common need for associating something with something else. A dictionary lets you do that, associate keys with values. The keys are very often strings, like someone's name, for instance, or a word. The values are very often also strings, or maybe numbers, phone numbers, or the like, or even structures, like persons that have not just names and numbers, but email addresses and student IDs and bunches of other information as well. In fact, in a few weeks' time, when we focus on databases, we'll return to this paradigm of having keys and values to get at interesting data that we care about. Well, where do you see these? Well, phone books, whether it's physical or virtual. In a phone book, of course, we've got names, ideally alphabetized by first name or last name. And then the value might be John Harvard's, for instance, actual number therein. So dictionaries are sort of everywhere, even though you might not in the real world think of them as such. But indeed, if you were to implement a phone book as a dictionary, it's sort of like these 2 columns, name and then a number. The catch, though, or rather the appeal of a dictionary, really is that you ideally want it to be super fast. And that was the goal of the phone book, too. I could either do the linear search, 1 page at a time. I could do slightly more intelligently, 2 pages at a time, plus an extra step to double back if need be. But log n, as of week 0, was as good as it got when actually searching for information. But what if I told you that there's maybe a way to implement this idea of a dictionary, otherwise known as an abstract data type that just has keys and values, but I could implement it with a data structure, an actual data structure that maybe actually gives me constant time. That's sort of the holy grail of algorithms and data structures. Can you build it so cleverly that there's no dependency on n? You can just get at data super, super fast, constant time. Maybe not 1 step, maybe 2 or 3, but super, super fast. And that's, in fact, where we'll focus for the remainder of today. Can we find this holy grail of a data structure and algorithm that gives us constant time access? And all we have to play with is time and space and maybe pointers and memory. I think we have all of the building blocks thus far. So how might we set out on this particular goal to achieve that? Well, let me give us one new building block or ingredient, which is this notion of hashing. So hashing relates to what's known as a hash function. And a hash function, like any function, takes input and produces output. And the idea of a hash function ultimately is that it allows you to decide where some value goes in memory. So for instance, here are, by design, 4 buckets on stage for the 4 suits of a deck of playing cards, for instance. So we have the spades, the hearts, the clubs, and the diamonds here. And if you had a deck of cards, like 52 cards here, we've got the jumbo version online, how might you go about sorting these in order from 2, 3, 4 on up to Jack, Queen, King with the ace either at the top or the bottom, depending on what you prefer? How could you go about sorting these? Well, you could kind of just spread them all out and start making a mess of things and figure it out. And it takes some number of steps to get through all of the cards. But a lot of us, myself included, would probably bucketize the values just to make a big problem the same as 4 smaller problems. Give me all the hearts, all the diamonds, and the other 2 suits in separate piles. And buckets is actually a term of art in computing. To bucketize something means to put a an input into a location. So what do I mean by this? Well, here we have the 4 of clubs, so we'll put this in here. The queen of clubs in here. 8 of spades here. And as I do this, of course, I'm sort of making the problem smaller and smaller so that at the end of the day, it's going to be easier to sort like 13 of these cards instead of all 52. So here we have the 6 of diamonds. We have a bug. So like this like, program would crash if you don't actually have a bucket for it. So that's sort of an exception. Here we have another 2 and a 10. And even though this is still going to take me 52 steps, I bet you if you timed me, I could sort 4 buckets of 13 faster than I could sort 1 bucket of 52. And that's sort of the general idea. Bucketization helps sort of take an infinite or a very large domain and map it to a smaller range of values. So from 52 possible inputs, or 53, into 4 possible range values. So that's actually a building block, an idea that we can use. And hash functions are simply math or code that does exactly that. Takes as input some value and spits out as output some other value. But the key is that you go from a large or an infinite domain, any possible number of inputs, to a very well-defined finite range of values, 4 in this case, for instance. And it turns out that if you're on board with this idea of using hash functions, code or math functions that take as input this and produce as output that, we can actually build something that are called hash tables using that. And a hash table, as we're about to see, is essentially like the offspring of a array and linked list together. It's somehow a combination of the two. So for discussion's sake, I'm actually going to draw an array vertically, which we don't normally do, but who really cares? These are just artist renditions anyway. So here's an array with 26 buckets, for instance. And suppose that I'm implementing a hash table that I want to ultimately store names of people, for instance, so that I can implement a dictionary, key-value pairs, or more specifically, a phone book. So again, here we see the distinction between a dictionary is this abstract data type that just has keys and values. A phone book is a specific example thereof. But a hash table is one way to implement a dictionary. Another way to implement a dictionary would just be a really long array, and you just put all the names and numbers in one long array. Or you use a linked list, and you put all of the names and numbers in one long list. The downside of those, of course, is that maybe it's big O of n, maybe it's big O of log n, maybe it's big O of n. But I'm talking about constant time now. I'm trying to take a step toward a data structure that maybe somehow leverages the best of both worlds, arrays and linked lists, and gets me closer to constant time. Constant time. Using hashing is one technique to get there. So here are 26 buckets drawn vertically. And let me propose that this location 0 represents the letter A. This location 25 represents the letter Z. So depending on someone's name, they're going to end up over here, or somewhere in between. I think that's not all that new, but it's an incarnation of bucketization. Instead of 4 buckets, I've got 26 buckets. And I'm going to use a person's name as input, specifically the first letter of their name as input. So how might this work? Well, here I've numbered them for the sake of discussion. Now let's more concretely use their ASCII letters that correspond, A through Z. And suppose now that, once you're on board with that model, I want to insert someone like Mario into this. Well, I think I'm going to put this at location 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Even though it's the 13th letter, it's 0 index, so Mario with an M ends up in this bucket here, so to speak. More specifically, in this array location. Everything else for the moment is null. Then maybe we insert Luigi. Well, L comes before M, so Luigi goes in this location 11 here instead. Maybe then we have Peach, who goes in this location here because her name starts with P instead. So this actually seems like a great system so far. We've got Mario, Luigi, Peach, and maybe all of the other Nintendo characters in here ultimately. How many steps does it take to look someone up? It's already constant time, right? Because if you give me Mario, I just know, OK, M, I can do the ASCII value trick that we did weeks ago. That's 12. Boom. I can jump in an array with constant time to a specific location, just using square brackets. You give me Luigi, I figure out L. Boom, there's Luigi. Peach, P, got it. There's her number. So already I seem to have a system, because I'm hashing on, not the suit of a card, but the first letter in a name that's given to me as a string as input. I can find you that name and presumably number in constant time. But this is going to mess up quickly, especially if you're a Nintendo fan. What could go wrong with this model with 26 buckets like this? Yeah.
with letter M or P or L.
Yeah, I mean, what's going to happen as soon as I have two characters whose names start with the same letter in the Nintendo universe, this is eventually surely going to happen. So far, I've gotten lucky with all of these other characters, but I do think, indeed, before long, I'm going to have what we're going to call collisions, whereby here, two L names somehow collide, and I need to deal with this in some way. Now, one way to deal with a collision in this sense was, OK, I want to put it here. OK, Mario's space is taken up. I can put it where the N names would end up going. But that's a little stupid, because now I'm just going to make a mess of things eventually if I just resort to randomness or first available spot. And I'm definitely not going to get constant time. That's going to quickly devolve into linear time, because it might be all the way down here if that was the first available spot. But what I could do, if I keep going, Link, for instance, just added in, no pun intended, I could kind of link all of the similarly named names together using a linked list here. And so this is why I say hash table is like an array of linked lists, because here's the array. It's kind of like your quick cheat sheet, your buckets for getting into some of the data quickly. But then if you do have collisions, OK, let's deal with it by just having any linked list that can dynamically grow and even shrink as you add or delete people from this address book here. Why a linked list? Well, I could use an array. I could use a massive two-dimensional array. But in your mind's eye, you could just imagine how much space you're wasting if you're pre-allocating 26 times 26 locations here, or something like that, just to have enough room from the get-go for these names. Let me go ahead and add a whole bunch of others from the Nintendo universe. Collisions are actually going to happen pretty commonly. And there's actually this principle in statistics known as the birthday problem, whereby if we surveyed everyone's birthday in this room, essentially with a small number of people in the room, we would have a very high probability of collisions. And so here, too, even if you don't recognize some of these names, pretty quickly do you end up having collisions in a world where you're just looking at, for instance, the first letter in someone's name. So unfortunately, this is not a great outcome. Why? Because imagine the perversion of this scenario. Suppose that we get really unlucky and every darn name in this world starts with L. Well, it doesn't matter that you have this array, and it doesn't matter that you're calling it a hash table. At the end of the day, this algorithm for a hash table could still reduce to big O of n. Because in the most perverse case, all n names are in the same bucket and the linked list at that location. So who really cares that you're calling it a hash table? You're not using 25, for instance, of the locations. But that's sort of a theoretical risk. Is that really going to happen in practice? Now, definitely with Nintendo, there's a lot of collisions here. But that's because my hash function is actually pretty naive. I chose a fairly simplistic hash function, but maybe I could be a little more clever about that. And in code, I could take into account more than just the first letter. So for instance, if I want to get closer to this holy grail of constant time access, let's just think a little harder and implement this data structure a little more intelligently. Well, first and foremost, it doesn't take that much effort to implement the code for this. Here again, as we've seen for a couple of weeks now, is how you might implement a structure for a person. Well, how might we go about implementing a hash table using typedef and struct and pointers, as we've now seen? Well, I would propose that we could implement a node for people as having a name and a number, just like always, but also a pointer to the next one. So in the picture you saw earlier where we had Mario and Luigi and Peach, each of them was this rectangle as I drew it. You can think of each of those rectangles as a person structure. But in addition to having a name and somewhere in there a number, there was also a little bit of space left over for the next pointer to someone else whose name starts with the same letter. So implementing this in code is actually not all that hard. And in fact, if you want to have a hash table of size 26, no big deal. Just say you want a table, or whatever you want to call this thing, of 26 node pointers. In other words, that vertical that I drew had 26 locations. Each of those was initially null, I proposed, because the hash table was empty. But it was really a list, it was an array of 26 pointers, because each of those could be the pointer to the beginning of a linked list. So this is how you could implement a hash table in code. Sort of one line, at least at a glance. You still need all of the functions to insert and delete and so forth. But this would really just be a hash table using all of the same ideas as in recent weeks. But what if we get a little smarter indeed about the hash function? So here's how we describe problem solving all this time. A hash function is just sort of the algorithm in the middle in this story. So if we input Mario as input, the output should be 12. If we input Luigi as input, the output should be 11, and so forth. But if that's the problem, we keep returning 12 and 11 and other such numbers a lot, well, let's not look at the first letter alone. Why don't we look at the first two, the first three letters? And I bet probabilistically we can drive down the probability of these collisions because there's not that many people whose names in the Nintendo universe start with L-A-K or L-I-N or L-U-I. That really lowers the probability of collisions by increasing, in this way, the number of buckets. And I haven't even drawn them all. Dot, dot, dot just means there's other combinations, permutations of English letters there. But I can just increase the number of buckets. Instead of 4, instead of 26, I could actually increase it to 17,000 plus if I do it in this way, looking at the first three letters. That would seem to really, really help. It doesn't make the code all that more complicated. Here, for instance, is how you might implement in C a pretty simple, if naive, hash function. Given a word, aka a string, you want to return an integer, like 0 or 1 or 2 or 11 or 12 or so forth. So we've seen toUpper before in the C-type library. Just look at the first letter in word, convert it to uppercase, just so the math is simple, subtract capital A, which we know is already 65. And this function, as is, will always return a number from 0 to 25. So you could imagine in your mind, we won't do it on the screen, but you could imagine just maybe looking at word 0 and word 1 and word 2, and doing some similar math and returning a number between 0 and roughly 17,000 instead to get back a much larger hash table instead. What's the downside there? Because I'm proposing that the code's not that hard. It's like a couple extra lines.
A ton more memory
What's the downside of having a bigger hash table wherein much less likely to have collision, but
a lot of empty
a little louder? Yeah. You're reserving much more space up front. In fact, the dot, dot, dots on the screen were really because I didn't want to draw a microscopic array with 17,000 locations, most of which are not actually going to get used. You start wasting space at that point. And it becomes a little silly because in the world of Nintendo, it's probably a pretty sparse universe, so to speak, whereby you don't have any names, to my knowledge, that start with AAA, let alone AAB, or AAC, or BBB. I mean, there's thousands of permutations that just are not going to be useful. So that maybe isn't the best solution instead. As an aside, you can also specify that these inputs are constant because as an optimization, you know that the words coming in are not going to change. And as an aside, let me propose that with an actual hash function, if you know the array is 0 indexed, you don't need to even return an int. You might as well return an unsigned value so that it's 0 on up, no negative sign, which would be an optimization here. But that still doesn't change the fundamental reality that adding more complexity beyond this is going to certainly increase, it would seem, the amount of memory that we actually use. So maybe the fundamental problem is that just looking naively at the first letter in someone's name is maybe not the best solution anyway. And in fact, at the risk of disappointing, the whole hash table, even when we use 3 letters of a person's name, technically speaking, theoretically speaking, it is still big O of n, because even though it's unlikely, you could imagine a perverse scenario where all of the names you insert somehow start with the same first 3 letters. There's no guarantee in this model that you're going to avoid that. What then is the appeal of a hash table to begin with? Well, if you've got 26 buckets, or heck, 17,000 buckets, let's call it k as a constant, well, really, if we get into the weeds, if you have a uniform distribution of inputs, that is to say, if you have a bunch of random names that are not all perversely starting with the same letters, technically, those linked lists that I described as coming out of the array are going to be probably on average n divided by k. Because if you've got k buckets, again, whether it's 4 or 26 or 17,000, on average, hopefully, each of those linked lists, aka chains, is going to be n divided by k. Now, we know from our discussion of big O in the past that if you have a constant value, like a number or a lower order term, who cares? That's still really big O of n. But here is now in week 5 where we see kind of a dichotomy between the theoretical running time of an algorithm and the actual wall clock time of an algorithm. The reality is, if you take the size of your data and divide it by 26, let alone 17,000, it is going to be way faster if you look at the clock on the wall or the time on your wrist than it would be if it were actually running in n steps alone. So yes, hash tables technically are in n divided by k, which is really just big O of n.
Doesn't
but
matter,
in practice, if you are smart and if you are clever about the hash function you use, and ideally use something that's more clever than just looking at the first letter, you can probably create, in the best case, an ideal hash function that somehow, magically, it would seem, ensures that you never have collisions. Because if you can find that ideal hash function, or at least a really good hash function, the probability of collisions is probably going to be so low that even if occasionally the thing devolves into linear time, most of the time it's going to be indeed constant time, aka big O of 1. So in short, hash tables, not really constant time, but with a good hash function, they can be pretty darn close to constant time. But there's one final data structure we thought we'd introduce today, this one pictorially for the most part, and that's known as a trie, which is somehow short for retrieval, even though that's pronounced somewhat differently. But trie just means it's a data structure for retrieving data. It is an alternative data structure via which, again, we can implement dictionaries, key value pairs. And to be clear, again, you can implement a dictionary with an array, a linked list, now a hash table, now a trie as well. But we get different running times based on those various structures. So a trie is a tree of arrays. You can think of it as. So frankly, all we're doing now is just kind of mashing together things we've already talked about and seeing what kind of weird Frankenstein data structure we come up with. But in this case, it's actually going to give us, I think, true constant time, but with a downside. So here's the beginning of a trie. And a trie is indeed a tree of arrays. And each of those arrays represents a letter of the alphabet typically, A through Z. So let me stipulate there's 26 boxes here written horizontally because I just want it to fit on the screen more like a typical array. And the way you use the arrays in a trie is to have an array of pointers. And if the person's name starts with A, you sort of use one of those pointers to point at another node, which is just another array for the second letter, and then a third array for the third letter, a fourth array for the fourth letter. And essentially, you use arrays for each of the letters in your input strings. So what do I mean by that? Well, here might be that array of size 26, A through Z. Suppose that we want to insert like Toadette into this data structure initially, or maybe shorter, Toad, for instance, one of the characters from Nintendo. So here is T's location here, and I've just highlighted it because if I have a word that starts with T, I'm going to actually change this null value to be a pointer to another array. And that second array shall be used to represent the second letter in this person's name, like O, and that letter is going to map to another array, whereby this location, A in Toad, points to finally a fourth array, whereby now at the D location, we have some kind of sentinel value, some kind of variable that says X marks the spot, a name ends here. So there's a way to do that in memory. But we're using 4 arrays, 1 for each letter, to map out the person's name. But we can go further. Suppose that there's another character in this universe, like Toadette, which is a superstring of this string. So it's a longer version thereof. That's fine. We can just add a pointer from the D location to another array, then from that array's E location to another array, then from that T location to another array, and from that array's E location, from that array's T location to a final array E. So in other words, each of these arrays is just an array of 26 pointers, or really 26 structures of some sort. And somehow in green, we're just indicating that a name ends here, and with the E, a name ends here. And we can do this again. If we have Tom, for instance, as a third name, we don't need any of these arrays. We can actually encapsulate T-O-M in the first 3 of those arrays. Now, suffice it to say, this is a lot of arrays. But what have we gained? Well, if you imagine this data structure getting crazy large with lots and lots of names and lots of arrays inside of it, it turns out that the amount of time required to look up someone's name or to insert someone's name has no dependency on how many names are already in the structure. Case in point, when I added Tom a moment ago, there was all of this bulk in the data structure already, but we didn't have to traverse any of that because we just go T-O-M, and we don't depend on how big the data structure already is. It does not depend on n. Technically, how much time does it take to insert or to delete or to search for someone's name in this? It would seem to depend only on the length of the person's name. So T-O-A-D-E-T-T-E. So I think that is 8 steps total for finding Toadette. 4 steps total for finding Toad, 3 steps total for finding Tom. Those are really small numbers, and if you imagine, there's surely some upper bound on how many characters are in the longest name in the world. I don't know if it's like 10 or 20 or 50 or whatever, but it is finite. It has nothing to do with the total number of words in this tree. And so the implication then is that the amount of time it takes to search for, to insert, to delete a name in a trie is by definition constant time, big O of 1. Maybe it's big O of 2, maybe it's big O of 50, but it's not dependent on n. Because as massive as this structure gets, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, that's all the steps it takes to find any of those names. It's dependent only on the length of the name itself, which has some kind of upper bound. So how might we implement this? This is probably the most common way. We just redefine a node in the world of tries to now be a structure like this that contains an array of 26 more pointers, each of which points to a node. And then we need some other value. I'm calling it char star number because I want this trie to be storing people's names implicitly and numbers explicitly. So if I want to store something like +19494652750, like John Harvard's number, I'm just going to store it as a string inside of this same structure. So a moment ago when I had the little green dots, the green dots in the array just meant that this string is not null. It's someone's actual number, which means if you see a non-null number, well, there's Toad's number. There's Toadette's number. There's Tom's number instead. This is a sufficient data structure to implement that notion of a trie. All we need, of course, is one pointer to the root of the whole darn thing. And so ultimately, like, we found our holy grail. Like, tries are, by definition, constant time. Because no matter how big the data structure gets, there's no dependency on how many elements are already inside of it. It has no effect on the running time per se. But it must come at a cost. What's the trade-off then for a trie? Space? What space? Yeah, the space to store all of those arrays. This is like the logical extension of not using 3 letters of a person's name, but every letter of a person's name. And the math there just means a massive amount of memory, because you need an array for every possible letter of the alphabet, would seem, even if most of those letters are not actually used, because there's just no name that needs those particular letters. So by significantly using more memory or space, you can significantly decrease time. And so that, too, is potentially a trade-off you may or may not want to make. So today was ultimately about introducing a bit more complexity, the last of our complexity in C, and these building blocks of pointers and memory to sort of stitch these things together. And I'll stipulate ultimately that the kinds of data structures we've talked about today, whether it's queues and stacks at the beginning, or linked lists in some form, or dictionaries, key value pairs, phone books, and the like, they're sort of everywhere. And even hash tables you can find in like Harvard Square or in New Haven as well. For instance, this is a photograph from this morning of a certain takeaway restaurant with which some of you might be familiar. Anyone know what place we're looking at?
Chipotle?
Sweet Green. So Sweet Green, a little salad shop in Harvard Square. What are you looking at? Like, this is a photograph of the shelves they use to distribute salads when you order them in advance online. But what really is this?
Buckets.
All your friends will be very impressed that you now see hash tables everywhere.
That's cool that you can see them in the real world.
A hash table. Why? Because when someone has a salad with their name on it that came out of the computer, they're going to put it in a specific location. This is location A through E. This is F through J, K through N, O through Z. And so they're hashing it to one of these 4 locations, not unlike one of these 4 buckets. Of course, here, they're not using really an array of linked lists that can grow endlessly. This is actually sort of like an array of arrays, because I can only imagine storing like so many salads on this shelf. And just imagine, I'm sure this happens during the busiest times. If you go in at like 12:30 p.m. and lots of online orders have come in, if they run out of space, for instance, in the A through E section, where do they probably put the next salad, even if that person's name starts with A through E? You know, maybe over here, maybe over here. Like, to my point earlier, you can kind of just plop things anywhere. And so the real world, like this data structure, might indeed devolve. But I do dare say after today, you'll start to see hash tables and trees and tries and all of these structures in different places. And hopefully what we've given you now in a CS class is sort of a mental model for the upsides and downsides of these structures, but also the technical skills with which you, too, can build them virtually as well. That's it for today, and we'll see you for Python next.
Woohoo! Nice.